Okay, so here on number 1, we're asked to calculate the change in entropy per mole for the melting of H2O, and we're given the delta H fusion, which we remember is the heat change per mole during the phase change between solid and liquid. So what we need to recognize for this question is an important equation for us. Here, delta S can be calculated. This is Q reverse in the numerator and temperature on the bottom in the denominator. Don't be distracted by reverse here. It's sort of a formality. It comes out of like thermodynamic theory. Basically, this is the heat change for a reversible reaction. But we can just ignore that and know that Q here represents heat change. In this case, and this is actually pretty tricky. A lot of the questions on this progress check are tricky. This is for a melting process. So we have to understand that the delta H fusion represents the heat change for this process because it is a melting process. And as I already said, delta H fusion represents the enthalpy change or heat change during the phase change between solid and liquid. Melting is a phase change between solid and liquid. So we have to understand that in this case, delta H is Q, because Q is generally just heat change for a process. So we're going to use delta H as Q. The temperature is given as 0 Celsius or 273.15 Kelvin, and we need that to be Kelvin for this and all thermodynamic equations. So we see here, simply just because it shows us in WebAssign that the answer needs to be in joules, that we need to convert this from kilojoules to joules. So just using the work that they're providing us here in the explanation. Here they're showing the conversion from kilojoules per mole to joules. We're just multiplying by 1,000. This is for no particular reason at all in scientific notation. This is 6,000 joules per mole now instead of 6. This is 273.15 Kelvin, which is the same as 0 Celsius. And that gives us our answer. They're giving us 2 sig figs here. It's reported with the decimals here. So we're just using this equation, and we had to recognize that Q in this case was delta H. Yep, and that's all. Just know that equation. Okay, let's move on to number 2. This is an intermolecular forces question showing up here. Thought it'd be important to go over it since it popped up kind of randomly. Okay, so for each of these, we're trying to determine which of the pair, A or B, has the higher melting point, boiling point, excuse me. And then also we're supposed to indicate which intermolecular force, hydrogen bonding, dipole, or dispersion, is the one that sort of makes the difference, is the one that tips the scales one way or the other. So boiling point, and again, this is sort of out of place because this is not in the thermodynamics chapter, but with stronger intermolecular forces, as intermolecular forces, I'm going to call them IMFs for the rest of this problem. As IMFs get stronger, boiling point gets higher and freezing point gets lower. So we'll just talk about boiling point now. So the higher boiling point among the pair A and B is going to be the molecule with the stronger IMF. Good bit to talk about here, I suppose. Hydrogen bonding is stronger, generally speaking, than dipolar, also called dipole-dipole force, and dipolar is stronger than dispersion. So basically, we're going to see examples of hydrogen bonding being stronger than dipole and dipole being stronger than dispersion, but then within examples of pairs that have the same stronger force, there's also trends there. Let's just jump into the problem here. So for row 1, we have NH3 and pH3. So NH3 shows hydrogen bonding, because hydrogen bonding intermolecular force involves a hydrogen bound to a nitrogen, oxygen, or fluorine. Here we have a hydrogen bound to a nitrogen. So NH3 has hydrogen bonding, whereas PH3 only has dipolar because it's a polar molecule. So A is has a higher boiling point because it has the higher intermolecular force because it has hydrogen bonding. Okay, so for row 2, we see here, because of this OH at the end of column A, that again we have hydrogen bonding because we have a hydrogen bound to a nitrogen, oxygen, or fluorine, in this case oxygen. And again, this is a polar molecule because of the oxygen-carbon bonds. But dipole-dipole force is weaker than hydrogen bonding. So again, we have A, and the force that determines that is again hydrogen bonding. For C4H8 and C10H20, both of these are just a bunch of carbon-hydrogen and carbon-carbon bonds, all of which are non-polar. So both of these bonds, both of these molecules, do not have hydrogen bonding, do not have dipolar intermolecular force because they are non-polar. But everything has, all molecules have dispersion force. And as molecules get larger, as is the case in this case with C10H20, as molecules get larger, their dispersion force grows. So B has a higher boiling point because it will have a higher dispersion force, stronger dispersion force. So dispersion is the force that makes the difference here. Lastly, HCl and F2. HCl is a polar molecule because it's a bond between a much less electronegative hydrogen and a much more electronegative chlorine. Actually, the difference isn't that enormous, but different enough. And F2, which is a non-polar molecule. So F2 only has dipolar or dipole-dipole force. F2 only has dispersion because it's nonpolar. HCl has dipole-dipole because it is polar, and all polar molecules have dipole-dipole. Therefore, it has a stronger IMF, HCl does. So the answer is A, and the reason is dipolar or dipole-dipole. Yeah, so that's sort of a review on intermolecular forces. That's actually a whole section of a chapter, so that's a crash course. But yeah, that's that. On to number 4. Okay, so at some temperature, the enthalpy and entropy changes for the reaction given here are given here. So we know the enthalpy delta H and the entropy delta S change per mole reaction here. We know it's per mole. Generally, when you have reaction as a subscript here, it means per mole reaction, but we also can confirm that because we have mole given in the unit in both cases. So A and B ask us for the enthalpy and entropy change per mole of iron, a reactant, and iron 3 oxide, a product. All we have to do in this case, A and B is pretty straightforward as long as you know this, and this is important. If we have a delta H reaction, per mole of reaction, and we have a balanced equation, well, we see that we need, per mole of reaction, we need 4 moles of iron. And per mole of reaction, we need 2 moles of iron 3 oxide. So to change these values and list them per mole of iron, we simply need to divide by 4, because the values we have here and here are per mole reaction, but per 1 mole reaction, we need 4 moles of iron. So per mole of iron, then, we'll just divide this total here and here by 4. And that will give us those values per 1 mole of iron. So here and here, we have just divided this value for enthalpy and this value for entropy by 4. And that's what we get here. Same thing for B, but we're dividing instead by 2 because these values are per 1 mole reaction, but for every 1 mole of reaction, we need 2 moles of iron 3 oxide. So we're dividing this and this by 2, and we get these 2 values. So not a lot going on there mathematically. I don't feel like I need to show that, just division. C, however, we're asked to give the enthalpy and entropy change per 0.165 grams of O2. Okay, so we have to do some stoichiometry here. We know that we have 3 moles of O2 per reaction, but this is a little more complicated because they're giving us a mass. We need to convert this to moles of O2 present. And then using this 3 moles O2 per 1 mole reaction conversion factor that we have here because of the balanced equation, we need to do some converting. And here we are doing that. So we start with that 0.165 grams O2, carefully noting that this is O2. So as we convert that to moles, we use 32 grams instead of 16 because, well, O2 is 2 atoms of oxygen, which equals 32 grams. So the formula weight for O2 is 32 grams. At this point, we've converted to moles of O2, and then we use that 3:1 conversion factor. We have 3 moles of O2, again, just based on the balanced equation here. 3 moles O2 per 1 mole reaction. And at that point, we have converted to moles of reaction, because depending on how many moles of O2 we have, and based on the fact that we need 3 moles of O2 to have a whole mole of reaction, we have now converted 2 moles of reaction. And we know from the thermodynamic data given that we have 1,775 kilojoules of heat absorbed per 1 mole of reaction. So there, at that point, we have successfully converted from 0.165 grams O2 to the heat absorbed in that reaction. So, oops, excuse me. That is the delta H, 3.05 kilojoules per mole. And we'll do the same thing for the delta S. We're just using a different value here for the entropy change in joules per mole Kelvin per mole reaction. So same thing, converting to moles of reaction and then using that delta S value. And we get negative 0.81 joules Kelvin. I think in both of these cases we should actually not have the mole there. It doesn't matter though. Not going to get in the weeds on that. So yep, that's what we do here. In this case, we just had to convert from mass to moles of reaction using the formula weight of O2 and using the balanced equation. All right, on to number 5. Okie doke. So here we are given a balanced equation, and importantly, we're given a Kp value. Remember, Kp is just the equilibrium constant in terms of partial pressure of the substances. So we're told to suppose that we start with 0.331 ATM H2, which is a reactant, and 0.371 I2, also a reactant, and that the initial partial pressure of the product, HI, is 0. So in this scenario, we have gaseous reactants. We have partial pressure from the reactants, but we have no products present yet. Okay, so is the system at equilibrium? And if not, will the reaction shift left or right to reach equilibrium? So here's where Kp is important. 43.1 is greater than 1. That means that the reaction is reaction is product favored. If K is larger than 1, Kp or Kc, then it is product favored. If it is less than 1, it is reactant favored. 43.1 is a very large K. That means this is extremely product favored. So this is not at equilibrium because basically Q, even without calculating anything, we know Q is less than K because Q, like K, is calculated by dividing the concentration of the products raised to powers of their coefficients by the reactants. Done the same way. There's no products, so right now Q is 0. We have 0 over some number. We don't even have to make a calculation. Conceptually, if there is no product present, then Q is 0. So we know that this is not at equilibrium because Q cannot equal K. K is larger than 1, but our Q must be 0 because we have no products, and that's in the numerator again. So we know that we're not at equilibrium. And when Q is less than K, in other words, when we have less products than is prescribed by K, that means we must shift from reactants to the right to products. We must consume reactants and produce products. So it's not at equilibrium, and it must shift to the right to reach equilibrium. Okay, so that's the easy part. B asks us to calculate the equilibrium partial pressures of each reaction component of each substance. This is a straightforward ice table problem. We're going to again use the explanation provided here. So this is our reaction, balanced reaction equation from above. And they told us in the problem that we start with 0.331 atm H2 and 0.370 atm I2 and 0 product HI. So that's what we put in our initial row. And then we don't have any ability to know how large the change step will be. So we just call it X. We have understood coefficients of 1 on the reactants and a coefficient of 2 on the product. So it's minus X, and plus 2X. Why did we use minus on the reactants and plus on the product? Well, it's because we already established earlier in the problem that we're going to shift from reactants to products. We're going to move from left to right. That means we're going to consume reactants. So it's a negative change for the reactants, and we're going to produce products. So it's a positive change for the product. This is getting lower, this is getting higher. Well, we don't know X, so we're just going to call this 0.331 minus X. And this is 0.370 minus X, and this is just 2X because it started at 0. And at that point, we have to do some, I believe, some annoying quadratic formula stuff. Let's see if and well, I'm just going to again use their work here. So these are our we have 2x over 0.331 minus x times 0.370 minus x. So this is our k expression here. I'm not going to spend a ton of time on this because doing the quadratic calculation is annoying and you generally don't have to do it on an exam. We're equal to 43.1 here because that's the Kp given. So K equals products, and that's raised to the power of 2 because of this coefficient, over reactants here and here. So we got to this step here because of foiling. We did first times first, outside times outside, inside times inside, last times last, and yep. And so what we're trying to do here is eventually get to this form where everything is on one side set equal to 0. And so to do that, we're going to have to multiply the denominator here times 43.1, which is why you now here have 43.1 times all of that stuff. At this stage, we have distributed that 43.1 to the 1, 2, 3 components of that per parenthetical in that parentheses. And then eventually we're going to subtract 4x2 from both sides. Then we're going to group like terms. So the x squared terms are together here. The x terms are together here. And the not connected to a variable terms are here. And yeah, and then we're going to plug that into, once we have it in this form, we've got a, b, c. Basically, a is what is connected to x squared, b is what's connected to x, and c has no variable. And then we're going to plug it into the quadratic equation right here. So just do that carefully. This plus minus here you do it twice. If you have to do this by hand rather than just, Googling it and putting in ABC, which is, let's be honest, what we're all doing here. You do this twice, one with a plus and one with a minus. You'll get two values. We're going to throw one of those values out because one of those values will give us a negative partial pressure. So basically, we're solving for x, and one of those x's is going to be larger than 0.331, which would give you a negative partial pressure. That's impossible, so we throw it out. We're always going to be able to throw one of them out for reasons. So anyway, once we throw one of them out, we keep let's see, where are we here? Yeah. So we keep this value for x, or rather, we keep the appropriate value for x and we plug it back into our ICE table to get the partial pressures. We plug in for x. And what we get for x is 0.2669. And plugging that back into the values in the ICE table, we are able to obtain our equilibrium partial pressures. So there you go. So a quadratic equation to get x. Then plug that value, 0.2669, plug that value back in here, here, and here, and then we get our actual equilibrium values. So that is how we do that. Okay, let's move on now to number 8. Okay. All right. So here we have a little bit of an acid-base stoichiometry problem. We're told that baking soda, sodium carbonic, I don't know the name of that molecule. Let's just pretend that I didn't just try to do that and not know the name of it. It's capable of neutralizing stomach acid, which is mostly hydrochloric acid. This is the balanced equation. What mass of baking soda is needed to neutralize 178 mils of stomach acid, having a HCl concentration of 0.058 molar? Okay, so this looks simple, but we do have to recognize that we have been given a balanced equation for this specific chemical process involving hydrochloric acid. And then they're saying, okay, we have 178 mils of stomach acid, and we're told here in the first line, one component, the majority component of stomach acid is hydrochloric acid, but not all of it. So it's important that they're giving us a volume and then telling us the concentration of HCl in that volume is 0.0538 molar. So very often when we're given a molarity, a concentration of molarity, and given a volume, we're going to have to use those two things in conjunction to get moles of the solute, moles of the component. And that's what we have to do here. We're going to have to do some converting to get to moles of HCl. And then the question wants to know how much NaHCO3 is required to neutralize, fully neutralize that amount of HCl. We have a one-to-one relationship here. So basically what we're doing is however many moles of HCl we have, we need that same amount of moles of NaHCO3 to neutralize it. Neutralize it just means to fully react with it. Okay, so 8. All right. So we're starting with 178 mils. Then we're using our molarity as a conversion factor, 0.0538 moles per, I just put 1,000 milliliters here. Of course, molarity is moles per liter, but I'm comfortable calling a liter either 1 liter or 1,000 milliliters, so I'm just using that so I don't have to build in another conversion step. And then using our 1-to-1 molar ratio of the reactants. So at this point, I know how many moles of sodium, of NaHCO3 I need, but the question asks for mass. So the formula weight is 84 grams per mole. of that molecule, and I end up at 0.8044 grams needed. Alrighty. Scrolling through there, I'm backing up to the previous problem. Because the math they use in the WebAssign explanation, this is that quadratic formula math. I just think that this shows it a little more clearly. Sorry to be backtracking. But here, the foiling that I was describing, I've listed it here before it's all combined. So this is first, outside, inside, last. And here it's combined. So just breaking that down a little more. And here I am showing multiplying 43.1 times everything in the denominator. And I think I'm showing it in a less weird way here. So this is what you get when you distribute 43.1 to all three. These are the 1, 2, 3 numbers you get. And here I have subtracted 4x2 from both sides, which leads us to A, B, and C here. So we've grouped like terms. I'm actually seeing here as a typo, I left there should be an X here and here. Sorry about that. There should be an X after this 30.213. But that's how I got to A, B, and C. And here I have actually listed everything in the quadratic. And these are the two values you get. And the reason we throw out 0.501, which is one of the two values you get, is again, if you put 0.501 in for X here, that'll give you a negative number. Same here. That's why we throw it out. You can't have a negative partial pressure. Okay, sorry about that. Just wanted to show that math because it's kind of hard. Okay, so now we're moving on to the second progress check on thermodynamics. And we'll start with number 1. We've got 4 questions on this one, so here we are. Okay. All right, so we have thermite, and we have basically just, they're saying some words, but really just giving us a balanced equation. During this reaction, surroundings absorb 1288 kilojoules per mole of heat. And we're asked, is this spontaneous? So this question kind of walks us through what we need to do in this little section here. We have to fill some blanks. First, we compute delta S entropy change for the system. And let's just pretend that's not there yet. From this, we compute entropy change delta S for the universe. Therefore, the reaction is blank under given conditions. So the whole thing here, we need to understand that when isolated, delta S, or change in entropy, it's spontaneous when it's positive and non-spontaneous when it's negative. That's because the universe trends towards increases in entropy, which is what, the first law of thermodynamics? Third? It's one of the laws of thermodynamics. The universe naturally trends towards greater entropy. And processes are spontaneous if they contribute towards greater entropy. But the actual delta S value we need to apply when determining if something is spontaneous or not in that way is delta S universe, not just delta S system or surroundings. There are 3 different values. Delta S universe is most simply calculated by just adding delta S system and delta S surroundings. So in this case, as we see here, we can calculate delta S universe by adding up delta S system, and in lieu of delta S surroundings, the way we're going to calculate that is by taking, and this is an important calculation for you to be aware of, we can take Q, again the change in heat of the surroundings, divided by temperature, and that will give us the entropy change for the surroundings. So we're going to calculate delta S system using the thermodynamic values that we have access to, and we're just doing products minus reactants. And we have to use our coefficients in the balanced equation to multiply that value as needed. And that's how we can calculate delta S system here. So we have the balanced equation. So as usual, the system is the reaction. More times than not, when we're dealing with system surroundings dynamics, it's a chemical reaction that is our system, the thing we're studying, the thing we're observing, that we're concerned with. So this is our system, this reaction. And we're going to calculate the delta S for that system just by looking up the delta S, the S values for all four of these substances. And then we're going to do products minus reactants. This is products on top here. And we're multiplying the value for magnesium oxide by 4 because of the coefficient of 4 here, and so on and so forth. So 4 times the value for MgO. This is actually the 4 we're concerned with here because we're doing products. So 4 times that value, 3 times this value because of this 3, and then divide all of that. That's all bracketed to become one value when it simplifies, minus the reactants. So 4 times Mg and just 1 times Fe3O4, which we have here. So we calculate delta S system that way, and we get negative 87.30 joules per Kelvin. That plugs into delta S system here. We are told in the product that 1288 kilojoules per mole is absorbed. Let's see. Yeah. Yep, the surroundings absorb 1288 kilojoules per mole of heat. So that becomes the Q for this process. And we divide it by the temperature at standard conditions. In thermodynamics parlance, standard is 25 Celsius, not 0. That's important. Always remember that. So our temperature is 298.15. And from here we can just calculate, and we get 4,232.67 joules per Kelvin mole. Important here, note that we built in the conversion step between kilojoules to joules there to get in the right unit. So that's our answer, 4,233 joules per mole Kelvin. And that goes here. Plugging back into these blanks, we had to get negative 87.3, which we calculated here for our delta S system. And this is a positive value. It's a positive delta S value. Entropy is increasing. Therefore, the reaction is indeed spontaneous under these conditions, because delta S is positive. Entropy is increasing, and that is spontaneous by nature. Okay, on to number 4. All right. This is a weird question, tough question, I think. We're given these 3 component reactions and their related delta G values. Then we're asked, what is the standard free energy of formation, delta GF? Formation is a type of reaction in which reactants synthesize together to form something, formation, for phosphoric acid. So the first thing you had to do here, and it's not immediately clear that this is what you need to do, you need to write the formation reaction for phosphoric acid, and then you can use these. You probably see this and you're like, oh, well, I need to use these reactions, but how? So for A, the first thing we actually need to do is write this reaction. This is the formation of phosphoric acid. As is often so important, if you don't know your acids and polyatomics and whatnot, you wouldn't even be able to confidently write H3PO4 as phosphoric acid. So keep studying that stuff. Once we do, though, we know we need to write a formation reaction that includes hydrogen, phosphorus, and oxygen as reactants. Shoot, you would have had to know that P4 is the standard form of phosphorus. Yeah, come to think of it, I mean, I guess you might have looked here and deduced that P4 is the form. This really is not something that you're like asked to know. Like, you're really not prepared to write this formation reaction, so I wouldn't stress about the fact that like you probably didn't know what to do here. But once you have this reaction, this formation reaction, you can look at the component reactions and realize that to make these, as we've done with Hess's law, to make these add up to having the correct products and reactants for your reaction, such that you can use these delta G values, you had to multiply this middle reaction by 3 because that gives you the 6H2 that you need here, for instance. So yeah, you multiply this middle reaction by 3 to get your formation reaction. That means you need to multiply your delta G value for the middle reaction by 3, as is happening here. And then you just add up all the delta G values, and then you get the answer to A by virtue of that, negative 4,519.6 kilojoules per mole. So yeah. And then B, how does your calculated result compare to what you could look up in a standard value chart? Well, so we fill in some blanks here. The listed value is actually negative 1316.7, which is a bit different here, right? Yeah. And then it's basically wanting you to recognize and understand that Gibbs free energy change, delta G, is a state function. And a state function, as we may remember, does not require, it does not consider, it is not contingent upon the path. State functions only, much like the just altitude of climbing Mount Kilimanjaro, the altitude is the same no matter what path you take. And that's like a state function. Whereas the distance traveled is dependent upon the path you take. If you take a more circuitous path, you will travel more distance and the length of your climb will be longer. So state just only relies upon the beginning and ending values, states, if you will, whereas a path function is affected by the route or the method, if you will, taken. So that's just a refresher on that. So delta G, Gibbs free energy change, is a state function. Being that it does not consider, is not contingent upon the path taken, any value difference, any difference in the values between what we calculated from these component reactions, this stepwise process, this multi-step chemical process, they must be, the value we computed must be a valid approximation of the actual value, and any differences must be due to the assumptions made rather than the path followed. So the whole thing here is, this is just like weirdly reinforcing that state functions do not depend on the path taken. So you can't say that any differences would have been due to the synthetic path followed, because state functions do not depend on the path. That's a pretty weird question. All right, let's continue. What was that, number 4? On to number 5. All right, so this is important stuff here. Again, we're sort of stepped through a problem with some fill-in-the-blank stuff at the top. For delta G to decrease with increasing temperature. So for delta G to decrease, that means to become more negative, right? Yeah. And processes are spontaneous when delta G is negative. So if delta G decreasing is another way of saying to become more spontaneous. For delta G to decrease with increasing temperature, delta S must be greater, equal, or less than 0. Let's take a look at something here. This is in the Thermodynamics packet. This is important stuff. When delta H is positive and delta S is negative, those processes are non-spontaneous no matter what. when delta H is negative, when delta S is positive, those processes are spontaneous no matter what. However, when they're both negative or when they're both positive, it's temperature dependent. And so like when they're both negative at low temperatures, it's spontaneous, but at high temperatures, they're non-spontaneous. So when they're both negative, for example, as temperature increases, the process is getting less spontaneous. But when they're both positive, as temperature increases, it's getting more spontaneous. So that's the backdrop here. So for delta G to decrease with increasing temperature, so for something to get more spontaneous as temperature increases, delta S must be positive, because processes that are where delta G is dependent on temperature are either when delta H and delta S are both negative or both positive. And among those two, the ones where delta G is getting more negative, meaning the process is getting more spontaneous, that happens as temperature rises only when delta H and delta S are both positive. So for our purposes here, we need a process where entropy is increasing or delta S is getting more positive. Those are the processes in which delta G is going to be getting more negative and the process is getting more spontaneous as temperature goes up. So that's the backdrop. So since we are not supposed to perform computations in this problem, it mentions that in the directions, we have to assume that delta S is directly proportional to delta N. So yeah, as we, in processes that increase the moles of gas from reactants to products, we'll have a positive delta N and a positive delta S, because if we're creating more gas molecules, we're increasing entropy, because gas is the most disordered phase. So for A, B, and C, we are decreasing the number of moles of gas, and that's just based on coefficients. Here we have 1 mole of N2, 2 moles of H2, both of those are gas. And in the products, we just have 1 mole of N2H4. So we're going from 3 moles of gas to 1. That's a less than 1. That's a negative delta N, so it doesn't meet the criteria. That's true for B and C as well. We're reducing our moles of gas from 2 to 1 here, and from 7 to 0 here. Well, actually 3 to 0. This is the only gas. Finally, for D, we're going from 0 moles of gas in the reactants, because this is a solid, not a gas, to 5 moles of gas in the products. So in that case, delta N is greater than 0, and therefore an increase in temperature will reduce delta G. Again, make it more negative, which is another way of saying make it more spontaneous, because processes become spontaneous when delta G becomes negative. And this reaction does meet the criteria specified above. All right, one more problem, number 8. Let's see. Number 8. So here we have some thermodynamic stuff. We have a sample of carbon burned in a calorimeter. If that calorimeter absorbs 97 joules per Kelvin during the reaction, and the universe absorbs 325 joules Kelvin, how much did the entropy of the sample change? Okay. So they're giving us an equation. I'll say that this is not a common equation. This doesn't pop up a lot, but it's given in the problem here. I thought I'd cover this just because it's an unusual question, really. Doesn't usually show up. The equation relating entropy change in a calorimeter to that in a sample, the sample in a calorimeter, is delta S universe equals delta S of the sample plus delta S of the calorimeter. Where delta S universe overall, yeah, we get that. Okay, so they're giving us the calorimeter delta S change. We have to use 97 joules. Well, actually, let's see, did 97? Yeah, so we've got the Q's for both of these things. In this case, we just have to assume that the values given are the delta S values. And we're going to use those and just plug them in for sample and calorimeter. So 97 joules Kelvin for the calorimeter and 325 joules Kelvin for universe. So this is just a rearrangement here. Just a rearrangement of this equation. We've isolated sample on its own. And we've plugged in for calorimeter and universe. Those are given in the problem. And we get 228. So just be aware of that equation. Yeah, and that's all you have to do with that. All right, those are the problems. Thanks for listening. Have a wonderful day. I'll see you soon. Bye-bye.